Hello, everyone. Okay, so now let's wrap up our discussion here of this lecture. So I think we should be able to finish this lecture with this third video here, and then I'll start our next discussion, our next lecture when we talk more about enthalpy, solving, actually using enthalpy in chemical problems. Okay. All right. So now let's talk about a second example. What if our system's not at constant pressure or constant volume, okay? Okay. All right, so let me just quickly glance over here. Okay. So now we're talking about the energy changes now for each system. So we're going to now boil down the energies for a system at constant volume and constant pressure. So we already did the example for constant. We already did the example for constant volume. So now let's go to constant pressure. Okay. All right. So okay. So the experiment in the second example, though, was not done at constant volume. It was done under conditions that we define as constant pressure. So in the second experiment, the interaction between the system and the surroundings involved both not only heat but also work. So in the first example, we didn't have any work. So nothing was lost to the surroundings. So to measure the effect of both of these quantities or path functions, we defined a new function, and this is called enthalpy. Okay? We call the state function enthalpy. So this symbol is defined as H. So you may have seen H before, that's enthalpy. So we usually call it the heat of reaction. So the amount of heat released by a reaction that's allowed to do work on the surroundings or at constant pressure. So usually reactions are, their energies are recorded at constant pressure. So that's all the enthalpy values we see. So by definition, that is what enthalpy is, the measure of the amount of heat given off or absorbed by a chemical reaction at constant pressure. Okay, so we're going to talk more about that. Okay, so for our example of a piston cylinder apparatus, in the second example, we can say that the change in enthalpy, which is delta H of the system, delta H of the system, is equal to the delta H of the, sorry, not delta H, my bad. So we can say the enthalpy of our system is equal to the change in energy of our system, okay, minus the work done or lost by the system to the surroundings. Okay. So when this happens, we say, okay, the concept of enthalpy is useful because it can show that the magnitude of heat given off or absorbed by the system at constant pressure is equal to the change in enthalpy of the system. So that's pretty useful. So in this case, we say delta H of the system equals the energy or heat of reaction transferred at constant pressure. So the magnitude of the heat is directly related to the enthalpy of the system. So if we have a chemical reaction, we can measure actually the delta H of reaction. And those are values we are interested in calculating the energetics of a chemical process and whether or not it's feasible or useful or not. So we get this equation, we get this form of the equation by saying that, okay, we know that delta H of our system equals delta E of our system minus work. But we know that all the energy of our system is either Q plus W. Okay, so it's going to be energy. All the energy of our system can either be energy from heat, or it could be energy that's given off or produced by work. So in this case, we have Q plus W minus W. So the energy that was done on the system by, um, say when the system gains energy, right? So that will be Q. But initially speaking, so before any energy was transferred, right, all the energy of the system was the sum of Q plus work previously, before any chemical change occurred. There may be, the system absorbed energy from the surroundings, and that's why, or it got compressed before a chemical change. So we say that the total energy of the system, conceivably possible, is either from heat or work done on the system. So in this case, since work is being done on the surroundings, we can cancel these terms out, and we get delta H system is equal to Q. So this is at constant pressure, and that's the equation we got below. Okay. So in this case, this work factor, remember, it comes from the pressure relationship we saw before. Pressure times delta V. So we just equate this to W, and that's where W came from. And since it's negative because it's expanding, the system's expanding against the atmosphere, we're going to do minus W in this case. So it's going to be minus W. So in this case, we get Q plus W minus W. Those cancel out, and then we say that the amount of heat released by the system is Q. Okay, so the delta H of our system is related to the amount of heat given off by the system or absorbed by the system. Okay. So any value of work that was previously there, it's canceled out by the fact that the chemical reaction is going to give off, is going to do work. Is probably going to do work against the surroundings, so that's why W is negative. Okay. All right. Now let's consider an actual process we care about, okay, as chemists. So let's think about this apparatus. Okay, so so in this example, we are just removing the hot brick, and we're not considering it at all. Okay, so now we have a mixture of ethane gas and oxygen gas, and then we're going to combust it. So a spark is introduced, and we're going to combust the reaction according to this chemical equation. So what can we say about it? Well, the temperature in the container will increase, right? Increases as a result of the energy given off in the reaction. So the temperature is going to increase because energy from the reactant is going to exit and be released to the surroundings, and that's going to not only increase the temperature, so that's not only going to be responsible for heat of reaction, but it's also going to be responsible for the work done. So any of the actual energy of the system before, it's going to equal the sum of the energy of the system, and then any changes in that energy, and in this case, the heat produced and the heat lost as work. Okay, so heat is okay, let's see here. Oh, okay, so let's answer this question. Heat is given off by the chemical reaction because, now let's write this, the sum of the bond bond strengths of the bond strengths in the products. I'm not gonna have enough room in the products. Okay, and the products is greater. Okay, so we have to write this somewhere else. Let's write it right here. Is greater. Sorry, I should have left myself more room. Is greater than the sum of the bond strengths of the bond strengths and the reactants. Okay, so we get a more positive, we get a faster reaction if so energy is released if the energy of the products, so basically the energy of the bond strengths is greater in the products than the reactants. When that happens, there's a net increase in the release of energy. So in this case, we go to a more stable product. Okay, so the amount of heat that gets released, part of it goes into heating the container, and then part of it goes into raising the piston or doing mechanical work. So we talked about bond strengths earlier, but we'll also see a way to calculate enthalpy based on the different bond strengths. So yeah, I may go over that in the next lecture. Okay. All right. So because this reaction is done under constant pressure, we say the heat given off is equal to the change in enthalpy of the system that occurs during the reaction. So we commonly call this delta H reaction. So delta H of our system here equals QP at constant pressure. Okay, so we say this is also, we just say, okay, if we have a chemical reaction, we just call this delta H of reaction. So that's, so the heat given off in this reaction is equal to our enthalpy of reaction. So that's how we can actually measure the enthalpy of reaction based on these enthalpy values, which only depends on the initial and starting point. Okay. So next time we will discuss calculating enthalpies of reaction and talking about how to use these enthalpies of reaction to derive chemical, pretty much heats of reaction, and how to use it in a meaningful way to chemists. Okay, so I'll see everyone next time.